Okay, in this video I'm going to look at some specific values that could have been used in the oil drop experiment, and I'm going to show how the things that he was able to measure, including the radius of the oil drop, the space between the plates, and the voltage, can be used to determine that charge on the particle. Once we do that, we'll also show that the resulting charge is a multiple of the elementary charge, and then we'll talk again about how he was able to determine what the elementary charge must have been. So here our oil drop has a radius of 7.07 times 10 to the negative 5 centimeters. I'm going to use that to come up with a volume in centimeters cubed that I can use the density to go all the way over to the mass of that oil drop. So the volume is 4/3 pi r cubed and if I put all that in, 4 times 3.14 times I get a volume of 1.48 times 10 to the negative 12 centimeters cubed. Now using the density, I can figure out, assuming that this oil drop has a uniform density, what the mass must have been. So 0.92 grams per centimeter cubed. You might have noticed that I left my radius in centimeters, which is an odd choice because usually we'd go to meters, but since my density is given in centimeters cubed, I just left it alone. That way it will be in agreeable units and get me my density or my mass without having to change any units here. So times 0.92 is what that works out to be, and my mass then is 1.36 times 10 to the negative 12 grams. Here we do have to be careful. In physics, we're typically assuming we're dealing with kilograms, so we do need to make the change here from grams to kilograms. So for every 1 kilogram, there are 1,000 grams. And doing that, I get a mass of 1.36 times 10 to the negative 15 kilograms. Now I'm going to come up with the force of gravity that would be acting on that oil drop. Mass times g, assuming we're on the surface of the Earth. 6 times 10 to the negative 15 kilograms times my 9.8 newtons per kilogram. And I get 1.33 times 10 to the negative 14 newtons. That force of gravity is being balanced if this particle is suspended by an electrostatic force, which is equal to the electric field times Q. So if this force of gravity is being balanced by this electric force, then I can say that Fg is equal to Fe. So using that, I can say that this is 1.33 times 10 to the negative 14 newtons. The electric field on a set of parallel plates can be given by the voltage divided by the distance between the plates. So here we have 200 volts divided by 0.012 meters. And I get 1.667 times 10 to the 4 newtons per coulomb. Times the charge. Now I can solve for the charge by dividing both sides by 1.667 times 10 to the 4. And I get 8.0 times 10 to the negative 19 coulombs of charge. So one more time, take the radius of the particle, come up with its volume, take the volume, come up with the mass, Mass tells me the force of gravity. If this is suspended between the two plates, force of gravity and electric force are equal. Since it's a set of parallel plates, the actual electric field is predictable using this equation. So get the electric field. And then the only thing, so I have the electric force, I have the electric field. The only thing I'm missing is the charge. So I can solve for the charge. Now this charge in particular must be made up of some number of the elementary charge. So this is 8.0 times 10 to the negative 19 times whatever our multiple number is, times 1.6 times 10 to the negative 19. So n here works out to be 5. So that's how Miliken was able to come up with very, very sensitive measurements of charge. And when he did this, every time he did this last step here, he always determined that n was a whole number. So all these charges that he came up with were always multiples of this number, whole number multiples. And what he decided then was that there was a basic unit of charge. He called it the elementary charge, E. And he found out that the value of that was 1.6 times 10 to the negative 19 coulombs. Today we know to interpret that as the charge on one electron, and that what he was seeing is that atoms were becoming charged by either losing electrons or gaining electrons, and since they couldn't lose half an electron, their charge would always be some whole number of electrons times the charge for one electron. So he didn't know that at the time, he just called it the elementary charge. He said that all charge must be a multiple of that. Later we discovered that that's actually the charge on an electron, and later than that, the charge on the proton.